We are going to be looking at a section called curve sketching. It's section 4.5. Going to look at basically how you can use calculus to sketch functions. I'm covering this because it's important, but I am not going to be giving you any test questions on these, and I won't be giving you any final exam question on this topic. The main reason is it takes too darn long, and it's not that difficult, really. And half of it is stuff that you managed to do or learn from 141. So what we're going to show you today is how can you use calculus to help you sketch a curve. And there are four main kinds of curves in the homework. And the first three questions are polynomials, and the next two are rational functions, essentially fraction functions. There's a trig function, and then there's a couple of mixed functions. Now, these are not exclusive. There are millions of functions in the world, but these are kind of the basic families. So let's start with 1, 2, or 3. Let me find one of the questions, and I will do this guide. And we'll kind of take you through the hit list of how you would sketch it. Which one will I pick? I'll pick 2, I think, if I find it. There it is. So, similar to question 2, we have a polynomial. This one is a cubic. And it looks like that. Now, here is your major hit list, things you need to calculate and find. Find the x-intercepts, find the y-intercepts, if there are any. Step 3, find vertical asymptotes. Would you agree that in this question, vertical asymptotes are silly? They don't exist. Horizontal asymptotes don't exist, so I'm not going to bother with step 3 or 4 for this function. Then we're going to finish off with local max-mins using first derivative, concave up and down and points of inflection using sine derivative. And we've actually covered these 2 stages in the previous section. So let's look at x-intercepts. Okay, from your 141 world, isn't x-intercepts found by solving when is the y-coordinate 0? Because when the y-coordinate is 0, you're looking at an x-intercept, which means I need to solve again, which means I'll need to factor it. Any suggestions for anything I could pull out as a common factor?
(3x).
That's what I would do. And that leaves you with an x squared. Take away a 6x plus a 9. In this particular case, I am left with a quadratic. And I get that. I don't know if I need to do that, but I'll do it anyway. Right. Oops, there's an x in there. Which means that I have 2 x-intercepts. An x-intercept at 0 and an x-intercept at 3. Not quite sure how big to make my axes, so I may end up screwing this up, but as I find things, I'm going to stick them on this. So we have an x equals 0, which goes here. And x equals 3 goes here. It's pretty much everything so far, right? Second thing I'm going to find is the y-intercept. And to get the y-intercept, don't you just make x equal 0? So in this case, y ends up being 0. So I guess we already know the y-intercept. It's that guy. So we really never get anything new out of this one. We're going to look for vertical asymptotes. There are none. We're going to look for horizontal asymptotes. Well, would you agree that this function doesn't really have a horizontal asymptote, doesn't it? Just shoot off to infinity. So there's none. And now we're moving on to local maximum, mins, increasing, decreasing, that kind of stuff. So local max and min. Now I have the original function in its untouched format. I'll now find its derivative per row. And I need to find critical numbers. And for polynomials, critical numbers are going to be where the derivative is 0. And so I'm now going to solve. When is this guy 0? And what's about to happen now is really just the same stuff we were doing last time. Can you remember critical numbers, a number line, pluses and minuses, and all that good stuff? Right? In this particular case, I'm going to pull out, I think, 9. And that allows me to factor, which tells me I have 2 critical numbers. One at x equals 3 and one at x equals 1. And then I'll do my number line. And on my number line, I will do the signs of the derivative. So this guy is 0 there, and the derivative is 0 there. And I'm going to cut some corners here. I'm just going to do it in my head. Essentially, the 2 critical numbers splits this into 3 regions. In each of these regions, I pick a test point. Once I choose a test point, I then find out what the derivative is, right, this guy here. And I only write down pluses or minuses, right? So that's kind of what we're doing last time. So I'm going to pick 0. And if you plug in 0 here, can you trust me that everybody's positive in that region? And then in this region, I'm going to pick 2. And it's, what is 2? It's still positive. Is that it? It's strange. Oh. Something's not right. It is negative. That's good. And at 4, it is positive. Yeah, I was a bit confused about this plus thing, but it was me. I did it in my head wrong. I mean, if you check it out, 9 times -1 times +1 is negative, right? It is negative, always was. Right, what do I have here? Well, positive 0 negative derivative means positive 0 negative. So that's a local max there. And at 0, 0, we have a local max. So like this. And it's not 0. It's at 1. Pretend that's not there. So at x equals 1, y coordinate is 3, 30, 12, 1 comma 12. So at 1 comma 12, that's there. That's where the local max is. And at this guy here, we have a negative, then a 0, then a positive, and that is a local minimum, and that's at 3 comma 0. And so I have a guy that looks like this. Right, that's not there, that was a mistake. I can pretty much tell you what the answer is going to look like, although my scale is really a little bit distracting. Would you agree that's basically the shape of the cubic? Local max bounces off there as a local min, continues in that direction forever. So there is a last step, but it's not going to tell me very much. And that is basically going to be concave up, concave down, points of inflection. Right, so I have the first derivative, and that's 9x squared take away 36x plus 27. So the second derivative is going to be 18x take away 36. The critical number then is going to be when the second derivative is 0. So I solve this fella. And I get x equals 2. And I create a similar table to the one up here. And I do some test points, but right now, there's only one critical number. Is it 2? If you pick a test point of 1, the second derivative is negative. And if you pick a test point of 3, it is positive. So at the point with an x coordinate of 2 and a y coordinate of whatever that damn thing up there is. So it's 3 times 2 cubed. Take away 18 times 2 squared plus 27 times 2. I get the answer, would you believe it, 6 after all that hard work. And what's going to happen there? Well, you have got negative, that's concave down, so it looks like that. Here it's positive, it's concaved up, it looks like that. The point of inflection is an x coordinate of 2 comma 6, which is there. You see that the second derivative really didn't bring much to the party. I kind of knew most of it already, but it's there because they want it to be. And that's our sketch. A little bit in the quick side, but half of that at the end, haven't we already done? Local max and min and concave up and down points of inflection. So that's not new stuff. And at the beginning, haven't we done x-intercepts and y-intercepts from Math 141? So we're really just putting together things that we knew to do one job, and that one job is this. So what does it look like in WebAssign? You get 4 pictures. One of them looks like that guy, and you pick the picture. So in WebAssign, all you do is you pick picture 1, 2, 3, or 4. So in a lot of ways, it's not, well, all the work that I use to draw it doesn't even get shown in WebAssign. All you do is show me a picture. Any questions about polynomials? Right, it's just time consuming. Can you see why I'm not going to have one in the final? I can ask you.
Yes, thank you.
I can ask you how to do in, I don't know. You know, tell me the local max and min of a polynomial. Can't I just ask you that question? And I don't need to all the other stuff around it. Okay, so that takes care of those three. Let's look at our next guy, question 4. And question 4 and 5, but I'm going to do 4, is a rational function, which again, you have done pretty much in 151, 141, I should say. Right, there's a rational function. I'm going to do something because I'm a picture straightener. And so the first thing I would do with a rational function, even before I started doing any of the calculus stuff, is I would factor it. And I would do that with a polynomial as well. And sometimes, not that often, this happens with a rational function. Can you see anything going on here that could make your life a little bit easier?
Cancel.
Yes. And what happens if you cancel an x minus 1 with a 1 minus x?
Get a negative.
And so what I'm really going to be sketching is that again. So what I've done is I've made the rational function a lot nicer. Now, because I have taken out an x minus 1 factor, right? Because x minus 1 and 1 minus x are allowed to cancel. Do you remember that trick that a minus b can cancel b minus a, but if you do, the answer's negative? That's what's happening here. That does mean a tiny, tiny little problem. At x equals 1, there is going to be a little hole in my function. So just remember to stick a hole at x equals 1 when we're finished, right? That's the only thing I need to do to be mathematically correct about that process. Right, now, I need an x-intercept, right? I need a y-intercept, so let's go through my hit list. And to get an x-intercept, can I just tell you x equals 0? Can you look at that right away? Because if you make that 0, isn't the top 0 and the top 0 is x? Now I want a y-intercept. Want the y-intercept be the value of the function at 0, which is 0. So all I know right now is that 0, 0, which is the x and the y-intercept, right? The origin. That's all I know. Now, vertical asymptotes. Does this thing have a vertical asymptote? Yes. Where is it? What's the equation of this guy's vertical asymptote?
Y equals 3.
The right number, the wrong variable name.
X equals 3.
Yes. Vertical asymptotes are vertical lines, and vertical lines are always x equals a number, because a vertical line is essentially all the points whose x coordinate is 3. Okay. Horizontal lines are y equals 3. And horizontal lines will happen when you have horizontal asymptotes, right? So this has a vertical asymptote at x equals 3. So 1, 2, 3. It's a vertical asymptote. Like that. Does this function have a horizontal asymptote? Some do, some don't. But does this one have one? It does. What is the equation of the horizontal asymptote of this function? It's going to be y equals a number because it's a horizontal asymptote. What number would this have? I'll show you how to find it. To find if there are horizontal asymptotes, you find the limit as x tends to infinity or negative infinity. In this case, now, do you know a guy that we've been doing not that long ago that allows me to find the limit of a fraction? It's a Belgian guy that should have been a doctor called L'Hôpital or L'Hospital. And he says that if you want to find the limit as x tends to infinity, differentiate the top and differentiate the bottom, and there you go. The horizontal asymptote is at y equals -1. You see how easy it is to get horizontal asymptotes when you have L'Hôpital on your side? Don't you just base it for a rational function? You just do this. So we have y equals -1, which is here, I guess. A horizontal asymptote. So far, so good. The next thing in my hit list is going to be increasing, decreasing, max min, that stuff, right? Which is basically everything that you can find by using the first derivative. So I'll return back to my function, f of x, is this one, and I will differentiate it. And pretty sure that you'll recognize that as going to be a quotient rule. So it's going to be f dash g, take away f of g dashed over g squared. So that's -1 times this guy, take away -x times 1. And that question is going to be over x, take away 3 squared. What do I get? I get -x add 3 plus an x over x minus 3 squared. And so I end up with 3 over x minus 3 squared. Interesting. Okay, let's find some critical numbers. Is there any value of x that this derivative function will be 0? Now look at the top. Could
There
that ever be?
shouldn't be.
No, it ain't going to happen, right? Now, since there's no 0 derivatives, doesn't that make this particular shape have no local max or local min? So I guess that's going to make it a little bit easier, but it does have an undefined. And the undefined would be at x equals 3. And I'm going to draw my number line. And there's my 3. And on my number line, at x equals 3, I'm going to put undefined. And I'm picking a test point of 2. And when I do it, it's positive. And when I choose a test point of 4, it's still positive. And now I have to figure out, what is that telling me? It is not telling me that I have a horizontal point of inflection, which would be that. And the reason it's not telling me that is that this is undefined. It is not flatline. We actually know what this is. Isn't it a vertical asymptote? So what you are telling me is that if you look at a point on the left-hand side of 3, you have a positive slope. So that means it's one of those vertical asymptotes that go up the way. And if you choose a number to the right of 3, this side, it is still positive. So it goes that way. Now, I know that curve is pointing downwards, but isn't the slope of it positive? So what this is telling me is the shape of the vertical asymptote. But it could have been a volcano, right? It could have looked like a hole in the ground. In fact, it's one of each. I actually know everything I need to sketch this. Shoots off to infinity, passes through the origin, and then has a horizontal asymptote. Shoots down to infinity, and then levels off. We're done. With one exception. At x equals 1, shouldn't have put a little hole. Are we good? Yeah, time is always an enemy in these situations. Right, next pellet in my list. Do a trig one. Don't have much choice. So question 6 gets it. And we're going to go through the same list with a trig function. And typically trig functions would have restrictions, but not all of them. When you do a trig function, the most common restriction is that x is between 0 and 2 pi. And the reason they do that restriction is that the shape just repeats itself. But they don't all have them. So here's one that doesn't. That guy. And in this particular world, I'm going to make my own restriction. The reason I'm doing that is basically, I don't want to draw an infinitely repeating function because they take a lot of time. So can't I just do one snapshot and say, that's the building block, and then just repeat it? So I'm making the restriction. Right. I need to know x-intercepts. I need to know when this fraction is 0. Well, that becomes when this is 0. And that ends up being at 0, at pi, and at 2 pi. At 0, at pi, and at 2 pi. Next thing I need to do is find the y-intercept. You just have to trust me on this, it ends up being the origin. Third thing we're going to do is look at this shape and see if it has any vertical asymptotes. If this shape is going to have a vertical asymptote, won't it happen when the bottom is 0? So I'm going to be trying to find out where does that happen. And this happens. And x is, where's the cosine of x, -1? In the range 0 to 2 pi. When is the cosine of x equal to -1? Uh-oh.
Hi.
Thank you. I was going to draw a little picture and kind of show you. There it is. Right. If you forgot, when you put it into Desmos and at least have a little look at it and see, oh, it's about 3.1. Oh, that must be pi. Hopefully you would do that. Ken, I don't know if I can explain this, but I know it's true. Would you accept that this thing just doesn't have a horizontal asymptote? Is it kind of obvious that it's just going to go up and down and it's never going to level off, right? It's just going to repeat itself. So that's the best I can do as an explanation. At x equals pi, we have a problem. Because at x equals pi, we have a vertical asymptote. But at x equals pi, we have an x-intercept. One of those two is wrong. If two things are, if algebraically two things are possible, but only one of them must happen, you can't have an x-intercept and a vertical asymptote. Agree? You've got to have one or the other. Who wins?
The asymptote.
Yeah. So this guy here isn't really there. But you didn't know that guy isn't really there until later on, right? Or I could have stopped drawing until I knew it, and then I wouldn't have to cross it out, right? So what are we going to do next is find some local max and mins, I hope, right? So original function, sine x over 1 plus cosine x. If we call the top guy f and the bottom guy g, we have another quotient now. We have a cosine times an untouched bottom. We leave the top alone and differentiate the bottom. And square the bottom. Distribute. You get a cosine x plus a cos squared. Multiply these and you get plus a sine squared. And you get a 1 plus cosine x squared. Okay. Any trig identities floating around that could make your life easy?
Cosine squared plus sine squared.
Would you get? You're right. What do you get when you
1.
1? Now here's something I wasn't expecting. What am I going to do then?
That's funny.
It is
It's
strange, isn't it?
1 over 1 plus cosines
Yes.
x.
Trig does that to you. Doesn't trig just do some weird stuff sometimes? And you just kind of have to go, okay, I wasn't expecting that. And I wasn't. I mean, I never did this question before today as a practice. Which does make life a little bit easier. Would you agree this shape has no local max or local mins? right? There's no place where this derivative is 0 because the top will never be 0. It does, however, mean that it still has a critical number. Doesn't have a critical number when the bottom is 0. Oh, we know this guy. Do you notice that the first derivative will find vertical asymptotes for you? Isn't critical numbers being undefined, isn't that also where vertical asymptotes are? I mean, other things as well, but vertical asymptotes are in particular. So I want to find out, using calculus, what kind of vertical asymptote? Couldn't it be a volcano? Couldn't it be what I call a hole in the ground? And couldn't it be one of the H things, right? So I draw a number line, put pi in the middle. Well, I better be a little bit more careful about my choices of guys. So I'm going to do those two guys, right? Boom and boom, right? So at this point, it's undefined. If I pick a half pi and I plug it in here, the answer is positive. And if I use my test point 3/2 pi and I plug it in here, the answer is positive. So I have a vertical asymptote who, if you go to the left of it, is positive, which means it basically is increasing, right? And if I choose a point to the right-hand side of it, it's positive, so it's increasing, right, as well. Oh, so it's another one of those one of each guys, isn't it? You see, positive and positive. I could go into the second derivative, but we're getting short of time. Plus, I kind of know most of what I've got, I believe. This shape here gets to about there. And this shape here gets to about there. Which pretty much means, doesn't this kind of look like a tan function? Okay, imagine my next 2 pi would look something like this. You know, if I, that's my building block, but if I picked this up and stuck it there, wouldn't it, it would look like, imagine this is the version I've got right now. If I duplicated that, wouldn't I get another one like this? And a guy like that. And if I duplicated it on this side, it's another one like this, and so on. So I pretty much know the shape. So, last guy in town. Well, I'll try and do as much as I can on the 5 minutes that we have. Choose question 7. This is basically, what do you do when you've just got a random function like that guy? Right. If you want its x-intercept, it's going to be at x equals 1. If you want its y-intercept, it's going to be the value of the function at 0, which is 1. Step 1 and 2. Vertical asymptotes doesn't have any, horizontal asymptotes doesn't have any, this particular shape at least. So now I can move into derivatives. Product rule. Differentiate this guy, you get -1. Leave that guy alone. Leave this guy alone. Differentiate that guy. There's our derivative. So what do I know right now about my function? No. I know it's x and y intercepts. It has a y-intercept there, and it has an x-intercept there. If you go looking for when is this derivative 0, it ends up being at x equals 0. Would you agree? And if I do my first derivative guy, I know that there's only a 0 derivative. This is never undefined. If I pick the number 1, it is negative. And if I pick the number -1, it is positive. So I am basically looking at a local min here. Right, local min. So far, so good. What else do I need? Well, I guess I could do the second derivative. And I just said something that is not true.
Should be max, right?
Say again?
Should be the local max.
Yeah, it's a local max. No, that's not orange. I think the shape actually does have a horizontal asymptote. And I think it has a horizontal asymptote, and I missed it when I said it didn't. So let me try and find it for you. I believe this function has a horizontal asymptote as x tends to -infinity. And I believe it's going to be y equals 0. So now I'm going to try and prove it. I'm going to find the limit as x tends to -infinity of that guy. That guy is not a fraction. I'm going to make him a fraction. Oops. Yeah. By doing that, I'm now going to use L'Hopital. Differentiate the top, differentiate the bottom. Now going to do brute force. -1 over -e to the plus infinity, which is -1 over infinity, which is 0. It does have a horizontal asymptote, and that horizontal asymptote is y equals 0. So now we have a major issue of putting the pieces together. It has to go through here, and it has to have a horizontal asymptote. And they sound like they're contradictions, but they're not. Couldn't I flatline it on this side without too much trouble? Right? I do have a kind of problem here, which is kind of throwing me a little bit. But here, it just keeps on going. And you might say, but you said it had a horizontal asymptote. I did, but notice what side it was on. It was only on the left-hand side. On the right-hand side, as x gets infinite, doesn't this just get infinitely negative? So here's a shape that only had a horizontal asymptote on one side. So I did manage to get all the pieces to fit, although it was it was almost like a broken jigsaw. It looked like it had a bit that wouldn't fit the hole. And that was because I hadn't realized until a little bit later that there was a horizontal asymptote on just one side. Now, if I wanted to test, is there a horizontal asymptote on this side? Because there might have been. Wouldn't I do the limit as x tends to infinity of this guy? And the only difference is that here it would have became -1. Well, it would have basically just been infinite. Right? You would have had an infinite number because 1 over e to the -infinity is the same as e to the infinity, which would have gave you the answer. So I am getting good at this. 45 seconds to go. So in the 45 seconds that we have left, I will very quickly show you something that I was hoping to show you at the start, but I forgot. If you go to Canvas, which is what I'm trying to find right now. So you say hi while I'm doing all this. I have something new in Canvas. I think I've got it ready. Here we go. Right. Are you looking at a Canvas page? You are not. Let me try it again.
Yes.
No, we can see it. I can see it now. You can see it.
Oh, it just took a few things to kick in. Okay, so do you notice there's a guy at the top that is new called Final Exam Practice Questions with Solutions? You see it? That is just a resource. It's
You
not
can't. I
homework.
can't see it anymore.
I think you took it
Yeah,
off.
you took it down after we.
Well, that's because you told me you didn't see
all
it.
right.
So I'm not. That's not my fault. You're getting me into a grumpy mood now. Can you see it this time?
Yes.
Yes.
Right. And I'm not going to switch it off now, right? You can see it.
Yes. We
Oh,
can
dear
see
Lord.
it.
Right. Final exam practice questions. This is not homework. This is things that you can choose to do. I would hope that you would do it. If you click on it, it gives you an idea of what a final exam is going to look like. You know yours is in a PDF. And basically you will get an exam looking like this. But your exam, as it says right at the beginning, is much smaller than this. But it does give you an idea of how I will ask the questions. So here are some multiple choice questions. So your test is going to look like that, but you aren't going to get anywhere near as many as that. You're going to get 10. I think there's 40 here. There's 20. Okay, there's 22 here, whatever it is, right? And then there's going to be a section 2, and you will do those kind of questions. And they are very similar to the test questions. And then right at the end, the solutions. So you can look at the questions, and I know you could do them as practice and see if you know how to do them, and then check the answer. Just, check yourself. It's not inclusive. There are going to be questions in your final that are not in that list, but it gives you an idea of the kind of thing. So what is your final exam going to be? If I gave you it as homework, if we did it in class, with the exception of a couple of things, for instance, there's not going to be any drawing graph questions like I did today, but I mentioned that to you, right? So that won't happen in the final. Do you know the questions? It has gone from me. But do you remember the questions where you had to do the limit as x tends to a of x cubed, right? The generic version where there were no numbers, right? And that would be an example of something I typically wouldn't do. But just because it's not in the practice does not mean that it can't be in the final, right? So, any questions? If not, bye-bye.